And I'm live. Well, South Africa does have a lot of white people, though.
Yeah.
To be fair.
A lot of people like.
Yeah.
They just like travel there and like Elon Musk.
No,
No, they're just born.
No, they were like born and raised there. Like it was like it was a colony of England, I want to say. Yeah. So. Yeah. All right. So here we are, back live with things to do. Now you are done with 75% of your school year already. Unbelievable.
We got like 45 days left.
I know, it's crazy. Now, a couple things to this. In regards to the third marking period, number one, third marking period did end on April 1st, the day before break. But grades are not due for teachers until April 15th. So we do have a little bit of time to get things in case you need to. Just saying. I do have some backlogged things that I have to grade. So if you've turned something in and the Genesis hasn't updated yet, please do not fret too much. I will get to what I need to get to. I posted on April 2nd, teachers are required to submit grades before April 15th, and we're currently on spring break. This translates to you having some extra time to get some things turned in. I am in no way done grading things, so do not worry if Genesis isn't updated quickly. Email me if you have any questions. So I posted that on April 2nd, just in case. I don't know if you saw that. But yeah, here we are. I have a few plans for today. Number one, I want to walk you through some more modular arithmetic and actually show you the first steps of how modular arithmetic can be used in order to encode messages, which is really nice. Then I do have, now listen very carefully, listen to my wording. It's the last Enigma challenge for part one. Yeah, I have one more Enigma project challenge for you for part one. And once part one is completed, that 13th challenge, there will be a summary assignment that you will have to complete for me using all 13 clues from the Enigma project. It's going to be wonderful. It's going to be great. You'll see that. I can see the excitement on all of your faces. Yes. The what? Sleepy? What's that? Try having two kids. Yeah, exactly. That's called having two kids. Anyway. Goodness gracious, Father of the Year. Anyway, so wow. If you haven't left a comment in the chat, please make sure that you do so. That'd be fantastic. And what I'm going to ask to start off with, I want to review a little bit of modular, and I want to show you our first steps into encoding and decoding things using modular arithmetic. So if you do not already have them out, I'm going to need those notebooks out and open. I got to do a lot of arm waving. I don't know why.
You were going to do that.
That's true. I probably was. Let me get the right file open. Because we're going to try and decode something using modular arithmetic. There it is, and there it is. I want to copy and paste this cipher. Yep, there it is right there. Boom. Copy. Close that. Open that. And then I can switch my screen over. There we go. Chapow. Make that a little bit bigger. 50. Oh, too big. 40. There we go. Now, here is a cipher that used modular arithmetic to encipher it. Now, you don't know what form of modular arithmetic was used in order to encipher it. But assuming that it was a monoalphabetic cipher, which it was, this monoalphabetic cipher could be deciphered using just frequency analysis. You could figure out what certain words are Like, for example, you could figure out maybe that this L would be an I or an A. Perhaps you see this ESP. This ESP, it could be the word and, or it could be the word the. You know, you could do anything with that and then extrapolate the rest of the alphabet from there. But I wanted to show you using modular arithmetic how this thing was actually done. Now, again, modular arithmetic, just to kind of recap that for you, and then we're going to decipher this once we get through that part. There you are. Cool. Today is the 13th. 41321. Here we go. Let's call this modular encoding. Modular encoding. Oh, and I really should have the chat open on my phone. Oh, I just got a message. Today is Joe Sarr's birthday. I did, but they said on behalf of the math department, and I was not a part of that. So
He's too good for that.
he's in the math department. Anyway, so as an example, give me a two-digit number, small two-digit number. 14. We'll go 14. Okay, we'll go mod 14. We'll go mod 14. And now give me a larger two-digit number. 25. Okay. 25 is the equivalent of 11 mod 14. 25 is the equivalent of 11 mod 14. Again, I just want to recap a little bit of what modular arithmetic actually is, and then we'll kind of use, okay, well, how do we apply it to encoding a message? The number 25 is equivalent to the number 11 mod 14. There are several ways that you can determine that. If I go to a calculator and I take 25 and divide it by 14, clearly it goes in one time and change. I could subtract that 1, and if I look at the change, multiply it by 14 and get a remainder of 11. We did that. This is a recap. It's been a couple weeks. This is why I'm showing it to you again. Don't panic. He took a deep breath. What it really means is this. 25 divided by 14 is 1. Multiply that, subtract that, 11. It's remainder 11. 1 remainder 11. I don't know when the last time you did long division was. Has it been a minute?
Yeah.
Okay. Well, this long division, the remainder shows what is equivalent to 25 mod 14. The remainder shows what is equivalent to 25 mod 14. What I did on the calculator, and I'll bring up the calculator one more time in a moment. What I did on the calculator is just a very easy way to do it without having to write anything. I did 25 divided by 14, and I got that 1 and change. I got rid of the 1, got rid of the whole number, I should say. And I took that decimal and multiplied it by 14 to get the remainder. That's probably the easiest, most straightforward way to get that calculation done without having to write anything down. And it shows that 25 is equivalent to 11 mod 14. What type of modular do we use for clocks? We use mod 12 for clocks, right? So, just another example of this. I could say it's 9 a.m. plus 5 hours is equal to, what is that? What PM? 2 p.m.? Cool. 2 p.m. 9 a.m. plus 5 hours is equal to 2 p.m. But 9 plus 5 is really what? 14. 14 is equivalent to 2 mod 12. Because again, you said with clocks, we do mod 12. And yes, we do. We do a modular of 12. Now, you could think of it in a couple of different ways. I mean, in reality, it's like, oh, it's army time, 1,400 hours. 1,400 hours minus 12 is 2 p.m. Cool. By the way, do you know why they call it AM and PM? The M doesn't stand for midnight. It stands for meridian. The AM stands for ante-meridian, and the PM stands for post-meridian. Yeah, the meridian is a vertical line on the globe, the prime meridian. You got to know these things. Yeah. But if I were to go to the calculator and do that same calculation, if I were to go to the calculator and do 14 divided by 12, it would clearly go in once. Remainder 2, which means it's 2 o'clock. But that's how the calculation would be done. That's how the calculation could be done. It's weird. In fact, check this out. It's just, I don't usually think of modular arithmetic in these terms. I usually think of it as like, give me a larger 2-digit number. A larger 2-digit number. Say again? 98. If I was going to do 98 mod 12, sometimes I just think about it in my brain as, okay, how many times can I subtract 12 until I can't go any farther? This is sometimes how I think about it in my brain. It's weird. 50. I know. Which is, again, I'm just going to show you the other alternate way of doing this. Minus 12, 26, minus 12, 14, minus 12, 2. It's another way of thinking about it, but like you just said, this is too much work, right? Yeah, it's way too much work, which is why if I was going to do 98 mod 12 and try to figure out what is the equivalent of 98 modular 12, I would just do 98 divided by 12, get rid of the 8, multiply that by 12, and get that 2. It's simpler to do it that way. Yeah. It's much simpler to do the modular that way. So again, this is what we kind of focused on before break. We focused on modular arithmetic, just trying to introduce to you the concept of a modular and how it can be used potentially to encode something. Now, there are 2 specific ways that I want to show you how modular arithmetic can be used to encode a message today. And one of them is like this. P plus N mod 26. Why mod 26? Well, because there are 26 letters in your alphabet. Now, obviously, it doesn't have to be, mod 26. You can have it as anything you want. In fact, there are other forms of like alphabets in the English language where you could have like capitals and lower cases and symbols and things of that nature. Like a keyboard or something like that. But we're going to stick to 26 as a very basic thing. The what? Oh, the classic. Nice. Yeah. The P stands for your plain text, just so you know. The P stands for your plain text. And in general, you are to assume that your plain text would be something like this. I'm not going to do all the letters of the alphabet for this example, but dot, 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 dot. There we go. I'll just do that one for now because we get the general idea. In general, a plain text is going to be written like this. Now, if you notice, I started with A being 0. I started with A being 0. That means the last 2 letters would be that. Notice, what are the numbers that I'm using?
26. Mod 26.
I'm using mod 26, but what numbers end up in this little table here?
25.
Well, no, technically 26 different numbers,
But it's included a 0.
including 0. Let me ask you this question. Kind of think about this in your brain. What is 26 mod 26? 0. Because 26 divided by 26 is 1 remainder what? 0. It's remainder 0. And again, I go back to this. The remainder shows what is equivalent. The remainder is what shows what is the equivalent number. So if you had the number 26 at some point for whatever reason, mod 26 would reduce down to 0. And we'll be able to do that. It's fantastic. So fantastic. So if I was going to be using this modular addition, is what they call it, this modular addition, is just an example of a Caesar shift. This modular addition is just an example of a Caesar shift. That's all that it really is. It's crazy to think about it in that fashion, but it really is. So, for example, I took a message. I took a plain text message, and I shifted it in the following way. I shifted it over 11. Now, what that means is that this plain text alphabet was shifted over 11 units. Or the numbers, let's say, the 0 was changed to an 11, the 1 was changed to a 12, etc. But everything was mod 26. So I have to create this brand new alphabet. Now we have our plain text alphabet up above, but now here is our cipher alphabet. Here's our cipher alphabet. Our cipher alphabet would be something like this. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I'm not going to do all the letters in the alphabet, but you'll see what I'm doing in a moment. 24, 25. Wait a minute, what do I do next? 0. Because wouldn't that be 26?
Yeah.
But it's mod 26. But it's mod 26. And this would be A, B, C, D, E, F, G. That's a G, not a 6. There we go. H, I, J, K, L, M, N, O, P. I'm going to do the rest down below in a moment. Let's see. LMNOP, Q, R, S. Did you know that the alphabet song is nothing more than Twinkle, Twinkle, Little Star? Someone explain it to him.
Same tune. Oh, I never knew that. That's why it sounds so familiar.
Yeah, I teach.
The alphabet song sounds familiar. Oh, that's so weird. So out of the ordinary to be familiar with the alphabet song.
Yeah. But again, if you notice this cipher alphabet, hold on, this cipher alphabet, it was shifted over 11 units. It was shifted over 11 units. And you could now see that, well, I have every number of 0 through 25. It fits perfectly because 0 through 25 is 26 different numbers, but everything is mod 26. So whatever number this was, for example, this number was originally what, a 25? This was originally a 25. Wait, I have it here. Here we go. Z was originally a 25 in plain text, but then 25 plus 11 is 36. 36 mod 26 is equivalent to 10. And you could think of it as, well, 36 minus 26, or 36 divided by 26 is 1 remainder 10. Yeah. Now, what's really nice about that, and I'm gonna actually post this link onto the Google Classroom in a moment, is that if you have something that is a Caesar shift, and this is literally just a Caesar shift, that's all that it is. If you have something that is a Caesar shift, then you can utilize the following. Where is it? No. Caesar shift online. I had the link yesterday. Was this it? Nope, that was definitely not it. Where was the link I used?
Somewhere.
Nope. It was that wheel thing. Caesar wheel. Decoder. I posted that link for you one time, didn't I? I'm fairly confident that I did. Let me see what I got here. I'm pretty sure that I did. Let me double check because I need to have the right link here. Let's see, Enigma. It was this one. There it is. Perkley. Nailed it. I'm going to post this link into your classroom. Perkley. Post. Boom. This is really helpful when you are doing a Caesar shift cipher. This is incredibly helpful. So if you go to your, oh, she did know that. Yeah. If you go to your Google Classroom stream, I posted this link. It is very helpful to have this Caesar shift right here so that we can decode the following message. So let me bring this one back up. Boom. Here we go. See if people can actually see that in the chat. Maybe I should change the font. Oh, no, I know what I gotta do. Hold on. Let's change this. Boom. You can probably see that a little bit better now. A little bit better. Not 100%. Oh, now they can, I think. Excellent. Yes. So I would like you guys to try to use that Caesar wheel. Use that Caesar wheel to decode this. See what you get. Now remember, that Caesar wheel was shifted over how many units? 11. Remember? So literally, wherever the Caesar wheel is originally, you could shift it over 11 units. Let me freeze my screen, make sure that works properly. Freeze. There we go. So if I shift this thing over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. We have those numbers now. Excellent. Yes, check this out. I'll unfreeze it. Chapow! I shifted it over 11 units, and notice now A is equivalent of what? P. A is equivalent of P. If I go back to my notes real quick, remember originally 0 was A, now 0 is P. But that's in the cipher. Oh, you want this. That's what you want. Once you get the first word, tell me what you believe it is, and then you'll know if you're on the right track.
Well, ESP is the.
Yes, yes, it is. Now, obviously, it's the word the, but then that first word is not the. But if you do get there, if you get the first word being there, then you were absolutely on the right track. Decode the rest. Now, obviously, there are other more interesting examples that I'm going to have for you in terms of this modular arithmetic stuff. This was just modular addition. Modular addition, like I said, is just a Caesar shift cipher. That's all that it is. And obviously, if you have a Caesar wheel like that, it's a lot easier to decode something if it's just been shifted over. How far did you guys get? Oh, you're on the last three words? The last what? Oh, are you going to beat him? See, the funny thing is you could actually like just figure out what the next word could potentially be just based on English and context and things of that nature. All right, you ready? No one's ready? There is a tide in the affairs of men, which, taken at the flood, leads on to fortune. That's what the message should have said in plain text. I'll say it one more time. There is a tide in the affairs of men, which, taken at the flood, leads on to fortune. It's a very serious quote for serious times. I don't know. We could probably Google it. Hold on. Just some guy, you know? Oh. Hold on. Let's see. There is a tide in the affairs of men. Let's see if that comes up with anything. Oh, it's taken from Shakespeare's Julius Caesar. Wait, what? Shakespeare's what? Yeah, I would think so. Like 400 years ago. Yeah, it's true. Anyway, so modular addition, like I said, is nothing more than a Caesar shift. But we have been able to create other types of monoalphabetic ciphers. In the past, you have created monoalphabetic ciphers by using keywords. You use the keyword like, I don't know, give me a keyword. Tomato? He said tomato. Yeah. Where it'd be like A, B, C, D, E, F, G, H, I, and then it'd be like tomato. So T, O, M. I can't use O again. I can't use T again. And I can't use O again. Double L. That's true. But still, if tomato's the word, tomato's the word. But then I would continue with, I would actually continue with the next letter, right? It'd be like N, O, I can't do O. P, Q, R, S, T. Oh, wait, tomato. Oh, you're right. Dude, I don't know why. I'm a math teacher, dude. Tomato. B, C, D, E, F. And then it would go on from there. That's the monoalphabetic cipher. But if we wanted something that was a bit more secure, perhaps we would pick a different word, word that was a bit longer, that it didn't have repeating letters. But at some point in that monoalphabetic cipher where you chose a key word, you would have to then match the rest of the letters in order. Fair? That's what we did in the past. But what if there was a way to just completely scramble all 26 letters in such a way where we did not have to memorize the order of the letters? And we would just know it using modular arithmetic. Yes. I'm just saying, wouldn't it be a bit more secure if we did a monoalphabetic cipher, but instead of after the keyword, the keyword right here, we didn't continue with the rest of the alphabet? It would be a bit more secure, wouldn't it? Think about all 26 letters just being completely scrambled up. How is that even possible? We couldn't memorize something like that unless... Kind of. I've memorized a system for recreating it whenever I want it. This is modular multiplication. Modular multiplication. Now, modular multiplication is very similar, but instead of P plus N, it's P times N. And in this case, we're doing mod 26 again. P times N. P, of course, being the plain text. Now, the plain text that we have, let's just do plain right here. Again, you just memorize the idea that 0 is A, 1 is B, and so on. I'm going to give you a tool for this in a little bit, but I just want you to write down at least the first set of numbers right here. Now we are going to create a cipher alphabet using the number 9 this time. P times 9 mod 26. Doesn't have to be 9. It could be any number you want, really. Just as long as the number that you choose is less than the modular, then you should be fine. Because think about it. If you did like if you did the addition one earlier and you did like P plus 26, it doesn't do anything. You literally just go around the alphabet once and end up back where you started. P plus 27. Well, that's really just P plus 1. It's the same thing. It's just, why would you do that, you know? So similar situation here. So I got a 9 here. What's 0 times 9?
0.
Yay. And then, well, 0 mod 26 is still 0. What's 1 times 9? 9. We did it. Great job, crew. Yay. But 9 mod 26 is still 9. It'll get more interesting once we get a few more numbers down the line. 2 times 9, 18. Now, 3 times 9. But I'm not going to write a 27. I'm not going to write a 27 because it's mod 26. It would be a 1. Now, here's the thing. If this is done correctly, then you will have all of your numbers in the cipher completely scrambled. Scrambled. And you will not repeat any of them. 4 times 9. Hold on. 4 times 9 is 36. What is 36 mod 26? 10. 5 times 9 is 45. Now, 45 mod 26. Again, like I said, you could go straight back to the calculator. 45 divided by 26. 19. Nine times 6 is 54. I'm going to go to an Excel spreadsheet in a moment. You'll see. Divided by 26 minus 2 times 26 is 2. This is what's happening to all of these numbers. Now, I'll do one more, and then I'll show you the table that I got. 9 times 7 is obviously 63. Divided by 24. My gosh. Divided by 26 is this number. Get rid of the whole number, multiply by 26, you get 11. Now, what's going to happen is that if you were to continue this for all the numbers in the plain text, if you were to continue this where you multiplied the plain text number by 9, modded it by 26, you would get a cipher alphabet where, again, 0 is equal to A, 1 is equal to B, 2 is equal to C, but it's all completely scrambled. You don't have to memorize a key word. Instead, you have this modular that does it for you. It is wonderful. Let's go to a spreadsheet real quick, because I don't know if you knew this, but Excel does have a modular function. Do you know that? So let's see. 0, 1, 2, 3. Let's put this down to 26. Or actually 26, 25, right? There we go. So I have all that. Is that too large? There we go. Cool. So now in this column, insert. In this column, I'm going to multiply by 9. So this would be equal to this times 9. If I do that, boom, it'll fill in the rest. Okay. Do you guys not know how to use Excel?
No.
Good Lord, there needs to be a class on learning Excel. Do you know how many things I've done on Excel that have made my life so much easier? I've kept track of like decades worth of fantasy football statistics on Excel.
Well, there's your problem.
It's insane how easy it is. Anyway, back to this. Now, equals mod. Now look at that. It says returns the remainder after a number is divided by a divisor. Let me zoom in on that. Holy crap. Zoom, zoom, zoom. Check this out. Equals mod. Look at that little statement next to it. Returns the remainder after a number is divided by a divisor. That's exactly what we're doing. This is what a modular arithmetic is. It's insane. Shut your face. So, mod of this number, 26, because that's the modular that we're doing, correct?
Yeah.
So now watch what happens. What were our first few numbers? It was 0, then 9, then... But I'm saying that it figures out the entire modular alphabet for you. And it never repeats a number.
Guys, I'm creating a new app. It's called Gmail, and I'm going to be rich.
Great job.
Don't steal my idea.
Okay. I'm going to be giving you guys this. I'm going to be posting this into the Google Classroom stream in a moment. But the thing that I want you to focus on is this row right here. Well, it's not the row of wisdom, but it's the row that we're using. It's the row that we're using. This is the multiplication table mod 26. It basically gives you the cipher alphabet for every single type of multiplication that you want to do to the plain text alphabet. And then it does it mod 26 for you, which is nice. I just wanted to show you what happens. But again, look at this row right here. Just notice for a second what it does to your plain text alphabet. Your plain text alphabet was originally A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. But now, with this new cipher alphabet, well, 0 is still A, 9 is J, 18 is S, 1 is B, 10 is K, 19 is T. Now, what I'm going to ask you to do, because I'm going to put this into my notes in a moment as well, I'm not going to ask you to copy down this whole table because I'm going to give you this table for future problems. But what I am going to ask you to do is this. In your notes, I want you to actually write out the plain alphabet and the equivalent of the cipher alphabet below it. I'm going to fill in this whole row on the board, but then I'm going to go erase it. But I want you to write this down into your notes because you are going to decipher something for me in a few minutes. I know. That's why you shouldn't use mod 13, number one. But number two, do you know why it does that? 13 divides 26. 13 is a divisor in 26, which is why that happens. Because remember, modular arithmetic is nothing more than finding the remainder after dividing. Yeah. So you really have to find a number that doesn't have any common factors with mod 26. L U D M V E N 22 is W 5 is F 14 is O 23 is X G P Y H Q Z and then I and then R. There we go. It's not perfect because it's still a monoalphabetic cipher. Monoalphabetic ciphers are susceptible to frequency analysis. But it's a much better system than just a keyword, let's say. But yeah, let me freeze the board and I'm going to send you guys this table. Freeze. Oh, yeah. Oops. Oh. There it is.
Now, Mr. Murphy, is there a limit to the amount of alphabet that you can add to a cipher?
That you can add to a cipher?
Yes.
What do you mean number of alphabets?
Instead of a monoalphabetic, it would be a 26 alphabetic. You'd have 26. So the first line of that could just be all zeros, and it could be a complete sentence.
Well, theoretically, but obviously you want to have a row that has 26 unique numbers in it. You know what I'm saying?
But who's going to be able to decode it? They're just going to think you're stupid if you wrote 15 or 26.
That's true, but then would the person that you're sending the message to be able to decode it?
They have the key.
But if they have the key saying it's all zeros.
I don't know anymore.
Okay. Again, the key being like 26, for example. What are the divisors of 26? 2 and 13. You shouldn't use 2. You shouldn't use 13. You should also not use 1. And there is no 26 up here. Oh, wait, technically there is. Yeah. You shouldn't use those. But also, you shouldn't have something that it has a common divisor. So you said 2 and 13, right? So anything that is a divisor of 2, if you're using mod 26, mind you, if you're using mod 26. If you're using mod 26, then you shouldn't be using these either. Yes, it does. Yeah.
3, 5, 7, 9, 11, 15, 17, 19, 21. Mod 26 kind of sucks, I'm not going to lie.
Interesting. If only there was a way in order to avoid these common divisor issues.
There's definitely a way.
Just keep going up.
If only.
Mod 1000.
Mod 27.
If only we were going to multiply by a number that didn't have anything, that we were guaranteed not to have anything in common with like 26 or any other larger number that we could have. If only there was a concept known as prime numbers.
I don't even know what a number is, man.
Prime numbers. Now, not all of these are prime numbers, but 3, 5, 7, 11, 17, 19, 23. 9's not prime. Yeah. So, using this alphabet, I want you to decode something for me to finish up class today. It's shorter. It is definitely shorter. Let me freeze my board real quick. go. And there it is. Copy. Paste. Let's match. There we go. Unfreeze. There it is. I'll get rid of the letters at the top. But this is what I want you to decode using that alphabet. It's shorter. And it's actually a little bit of a joke, which is hilarious. What you missed was I talked about what multiplication you shouldn't use because you wouldn't get a full set of 26 numbers. This one we would. It had to do with whether or not it had a common factor of 26. But one thing I did say, well, to avoid a common factor of 26, perhaps we would need prime numbers. That's kind of a hint into the future. Prime numbers. You guys ever heard of the seed of Eratosthenes?
No.
You know what a sieve is?
Yes.
What's a sieve?
So good. Calendar.
Yes, I guess you could say, sieves were more commonly used during the gold rush to kind of shake out the water in order to get the gold.
I'm Italian. I
What?
don't know what. I don't know. I only know pasta and meat sauce.
Okay. But you know what a sieve is? The sieve is used to separate things from each other, right?
Yes.
Well, the sieve of Eratosthenes is what you throw all the numbers into, and you shake it, and when everything has fallen out below it, what should be left in the colander should be prime numbers. Now remember, you're decoding. So the letter S should go back to the letter C, just as a heads up real quick. Right there, the letter S should go back to the letter C. There are a couple of disadvantages here. There are two letters up here, A and N, that actually go back to themselves, which is really weird. Huh.
7 problems. 7.
When somebody gets it, let me know. I want to hear the joke. You got to get the whole thing.
That's a good joke.
Hilarious. Would you like to say it? Why not?
It's not fun. It's not like I'm not very talkative.
not? Have you? Do you know who you are? Who else got it? Read it.
You actually
Read it.
cells are the best mathematicians because they divide.
Woo! Hilarious. Cells are the best mathematicians because they divide. Amazing. I know. Now, we are going to be sticking with modular arithmetic for a little while now, because there are other things that I need to show you in terms of modular arithmetic, in terms of sending messages to each other and trying to keep keys hidden. Because even if you sent this message to someone, they would need to know the key to unlocking it. And the key being that you used modular arithmetic times 9. Or you did times 9 mod 26. That's the key. Once you understand that key, you can decipher this message to be that hilarious joke that is award-winning. It's an award-winning joke.
Did it win a Grammy?
I don't know. Yeah. But we will continue with that next time. Now, as for the rest of you, I am going to be assigning you the last Enigma project part, or of the first part. You should be able to handle it. Should be. But then I will also be letting you know, or giving you on Google Classroom, of course, the wrap up to part 1, which involves a little bit of a research into our enigmatic character, which we're going to get to. Anyway, if you haven't left a comment in the chat, please make sure that you do so. And we will pick up with this on Thursday. Gosh, share that joke with a friend. I'm sure they will love it and thank you forever. There's the bell. Oh, man.